Okay, good morning, everyone. Looks like it's 10 o'clock a.m. on my clock. Welcome back to the third of our 3 webinars this week, where we're going to talk about the concrete mix design process and the JMF submittal or approval process. We're gearing today's talk primarily towards local agencies and understanding what they need to do for their MDOT related projects, ones that have perhaps federal funding or go through an MDOT letting process. With me this morning is Dave Cook, who is our Assistant Director of Certification and Training. Dave has a wealth of experience in concrete testing, as well as soils, aggregate, and asphalt, working for a number of consultants and testing companies in his career. And so we're happy to have him on board. He came on board almost a year ago, just under a year ago now. And so he's very knowledgeable in the mix design process, JMF submittals, and things like that. Again, I'm Steve Walkus, Director of Engineering, West Michigan for MCA. I'm going to kick it off. Dave's going to cover the middle, and I will wrap it up at the end. We should not go much longer than an hour today. But we definitely have time for questions and answers at the end, or if you'd like to pose any questions during the presentation, we should be able to stop and address those either with the presenter or the other MCA staff that are listening in and keeping an eye on the question and answer window and the chat window. So please feel free to use those in the Zoom software, the Q&A and chat, if you have specific questions you'd like to ask of us. All right, that's pretty much all I have for introductory remarks. We will get going here, and then I will pass it off to Dave after a few introductory slides here. So what we are going to cover today, we're going to talk about MDOT specifications and concrete grades. Again, we did cover that on Tuesday. But how that applies to the current specifications and obviously what they will be when the 2020 spec book is actually implemented. We'll talk about the basics of concrete mix design as far as the ACI process. If you were to have to develop a new one, just the highlights of that, not in detail, just the main points. We'll cover MDOT's JMF submittal form, which is form 1976, that needs to be filled out for each mix design or JMF that you plan to use on a project. So a lot of projects will not just have just one JMF used for it. There'll be a number of different mix designs or JMFs. So we'll cover that and the required documentation that should be submitted with that information for approval. So starting off, all materials that go into any concrete need to be from MDOT's materials source guide. They need to be approved materials from the qualified products list or an approved source. So that is typically updated every 6 months with new products added and or old ones that are no longer available or no longer in our market taken off. And so the current one at the time of bid, obviously this is a screenshot of one from 2016. There is probably the latest one from early 2020, I believe, in there still. But it's under the reports, publications, and specifications. It's one of their manuals or guides. They kind of have it in that portion of their website. They try to do it quarterly, but at least twice a year it is updated. So obviously the main product that goes into our concrete that binds everything together, the cement. All the cement producers that are available to ship to Michigan, products that are available in Michigan are listed on that QPL or material in the material source guide. So all those approved manufacturers are there, listed either as a type 1 or type 1/2. MDOT's spec in the spec book that covers cement is section 901. It's in division 9, which is materials. So it's section 901. So how do people get on that list? MDOT looks at mill reports from that producer for compliance to the ASTM spec. ASTM C150 is what MDOT uses. And they also want physical samples to do some testing on. And then after you're on the list, what they do is check mill reports submitted biannually, and then every so often random samples taken in the field for a QA verification of those same tests in the lab with just the cement powder primarily. Note here, type 3 cement, high early, type 3 per ASTM C150 is not allowed on MDOT projects. It's not very much different than a type 1 or type 1/2, which those are the ones that are typically available in Michigan anyways. It is typically ground finer, so it reacts faster for a high early mix. Supplementary cementitious materials we talked about yesterday also are listed on that in that source guide. For high performance concrete, it requires a minimum of 25% supplementary. That could be fly ash or slag cement. We do not use that much silica fume in our concrete. We typically use a max of about 8% silica fume. But all of those approved manufacturers are listed in that source guide and under 901. Very similar process to get on that list and to stay on that list as far as the lab testing to get on with some past mill reports, and then continuing submitting mill reports to stay on the list, and random samples every so often from the field for QA verification. For aggregates, most aggregate producers that typically do a lot of MDOT work go through the pre-qualified aggregate program, where they're a pre-qualified source. That requires yearly inspection of their labs, history of a good process, and spec compliance, and the QA testing then done on that aggregate just to be on the list is one test per 10,000 tons produced. If you're not on that pre-qualified list and you do choose to use your product in an MDOT project, then your testing is approximately 10 times what the pre-qualified ag producers have. You have one test per 1,000 tons. And that is either if you're a new source or have not been on that list in the past. And that's just the general testing to get on in the Division 9 for the gradation, as well as all the physical testing that's done depending on the ag type, if it's a sand or coarse aggregate or intermediate, with LA abrasion and freeze thaw dilation and those types of things. Fine aggregate, we talked about this earlier in the week as well, requires ASR testing, so sand sources need this testing. Again, the short test, which a lot of people fail anyways because it's very aggressive, is still in the spec. The one that is more reliable is the year-long test, the second one listed there, 1293. But again, it takes a whole year to get data on that sand source. So every other year, these sand suppliers should be running that ASTM 1293 test. In the absence of either of those, then you need to run the mortar bar test on the actual mix design using that supplementary cementitious material or other mitigation technique. Admixtures, as far as approved materials, same thing. They have to get on the qualified products list in the material source guide. They have to submit test data using 3 locally available cements that their product works well with those 3 cements that are available in Michigan. We don't want adverse chemical reactions going on in our concrete, but that's required for your air entrainment, admixtures, water reducers, accelerators, retarders, and those are 2 different specifications, ASTM C260 versus ASTM C494, and then a yearly affidavit from the manufacturer stating that those products are still in compliance with the required specifications. What MDOT wants to avoid is a witch's brew, which is when you're adding all these different chemicals, particularly from different sources, different manufacturers, where there's an unknown, possibly an unknown reaction going on, and not all chemicals from different manufacturers will play well with each other when they get introduced into the concrete. So if that is the case, then that ready mix producer would have to submit some test data with the different manufacturers' product being used in their mix, showing that I have a history of compliance and good test data. So where do mixes originate? Where does that come from? How do we decide where that mix design starts from? You can have contractor provided mixes or through their supplier, where they have historically may have been based on a standard MDOT mix, but the contractor is responsible for submitting that mix documentation, the prime contractor. So they may get it from the concrete sub, who gets it from their concrete testing, agency, and who may get it from the actual ready mix producer, who may get some information from their aggregate supplier and their admix supplier and their cement supplier. So it goes through all these hands and eventually ends up for review once you get the full package of information. There are some mixes where MDOT will spec the actual mix design, non-standard mixes, structural patching, project-specific pre-stressed concrete, bridge deck overlays where they'll actually spec the recipe that they want and or small quantities. But in a lot of cases, a lot of producers and or contractors have the flexibility to tweak their mix to suit their needs, as well as then obviously the test data shows that it meets the required tests at the particular age. So as far as developing that mix, contractor, again, through the prime contractor, they're the one that holds the contract with the state or the local agency. They send that mix design and proportion information with the supporting documentation. We'll get into all that a little bit later. And there are 4 main methods of coming up with those mix designs. Method 1 would be a new one, essentially. It requires trial batches. So you have a mix that you've never used that particular stone, that particular cement, that particular admixture, etc., or the combination of those in particular ratios where you don't have any test data. You've never done it. So it's a new mix design. You got to run trial batches. And then when it comes to the project, obviously you have to use the exact same materials that you ran with the trial batch. Method 2 would be the same mix. And that is where you have a concrete producer that has used that exact same mix on a previous project. So they have test data, QC and or QA test data from that mix, the exact same mix. So they can it doesn't have to be from a lab as far as the testing, I should say, it doesn't have to be from a trial batch done in a lab. It can be from the field. So a field sample done on a pour somewhere else with the exact same mix, and you get that test data fresh as well as hardened concrete test data. Method 3 would be a similar mix, that you've used that exact same mix except with one change and allowed, and that is the similar aggregates. So if it is a limestone coarse aggregate, but you're changing to a different source of a limestone coarse aggregate, geologically it's the same, then you can switch those out, but you have to be using the same cement and the same admixtures. And then same thing with the sand. You can switch out a sand, except that you do have to have the ASR test data on that sand. So that is one big requirement on that sand. So that's the similar mix. Method 4 is an annual verification. That's where MDOT essentially provides the recipe, and all you do have to submit is the certification information on the plant itself, and then you use the exact same materials that are being specified by MDOT for that particular recipe that they want. That's not very common. Again, mostly MDOT has gotten out of the mix design business, and they're leaving it up to the ready mix producers or concrete producers and their testing consultants to do that test data, develop that mix design, and submit the information to MDOT for approval. And again, in all cases, it needs to be from an MDOT approved source. All the materials must be from approved sources. So again, we covered this on Tuesday. This has actually been superseded by the QCQA special provision. This is the screenshot of the mix design requirements for concrete pavement mixtures. But it's, they break it down for the structural mixes, break it down by slump and strength, both. Instead of making one really, really long or wide table to fit it in the book, they actually cut it in half. So it's obviously the left half of each of those tables is repeated. But again, this has all been superseded by the QCQA special provision. The local agency version. Right here, you see P1M and P1 are paving mixes. DM are bridge deck, typically. T for TREMI, S1, S2, and S3 for different grades of structural concrete based on design strength. You can see the strengths, minimums required for the lot as well as for the individual test result. It's just 500 psi less. Maximum water cement ratio of all those is 0.45, and then the cementitious material contents range depending on the grade that you're using. And then it tells you the air content 5.5 to 8.5, and slump is in a note in the table, and the section number references the item that's being used to build with that concrete, that's being built with that concrete. So 602 obviously being concrete paving, 706 concrete bridge structures, and so on and so forth. Then the difference here, that table was from 604A, which is the local agency specification that most of you on the call are probably more familiar with. On an MDOT project, they use 604B because you can see they add a top line to that table when it's in the 604B special provision, because they they pay a bonus on concrete strength and air for MDOT projects only. They don't pay local agencies do not pay a bonus for concrete strength. They just have to meet the minimums or the ranges required. For the bonus, you have to do a percent within limits analysis for MDOT projects. So this will be your interstate routes, your M routes, and your US routes only, where they use that top line. So again, that's only for paving. That's the only time they do that bonus situation is for paving. They don't pay any bonus or concrete quality initiative, I believe, is what the pay item is listed at when you look at the pay items in the proposal. But you don't pay any bonus on deck mixes, which is the DDM section of the table, TREMI, or any other structural mixes. So again, we talked about this on Tuesday. P1M high performance concrete pavement will be called 3500 HP. P1 and P2 could potentially be used on a project. P2 for shoulders, P1 for any your non-mainline, or if you spec a non-high performance. PNC is your patching. That's not going to change. That note that says that it's 3500, that it was from an old version. It's still going to stay as PNC, and M is going to stay as it is as well. And then your structural mixes, S1, S2, S3, all based on design strength now, 4,000, 3,500, or 3,000, and your S2M for high performance structural bridge work. Your bridge decks and bridge railings, 4,500 PSI is the design strength, so that'll be called 4,500. Your high performance bridge decks and railings, 4,500 HP, and then TREMI will be 3,500 as well, just for underwater placements. So here's a screenshot of the Form 1976, the JMF form. All the numbers that go on this form are essentially from the concrete producer, either them directly or a testing consultant that is taking their information and filling out this form for them. But it has information, obviously general project information on the top, and then those 3 columns for coarse, intermediate, and fine aggregates. If you do not have an intermediate aggregate because you're not using a high performance or optimized mix, then that middle column about halfway down is not being used. You just have coarse and fine. And then the information on your cementitious and admixtures. And then at the bottom, the mix proportions. The old version of this form had aggregate bulk density values for loose pour or dry loose procedure. MDOT has switched to the dry rotted procedure, not the shoveling procedure, which results in values that are about 10% greater than may have been used in the past. Most have adjusted to this and have switched to this. When the switchover occurred, it was a bit of confusion because MDOT's guidance was still based on the other version of that test method. And the 2 versions result in, like I said, values that are 10% different than each other. Most, again, have adjusted to this, and so they do have the option for that on that form. So that's one thing to note, that if your aggregate bulk density values are not in the range that are recommended, it's because perhaps the other procedure was used to determine that number. ACI 211, which Dave is going to go into, is based on dry rotted. which actually gives more compaction effort to the stone when you're doing that density test. Speaking of Dave Cook, I will allow him to take over control here. Oh, share. I'd hit stop share. There we go. Instead of give control of the share to Dave.
All right, I think I got her, Steve.
Let me mute a sec. I'll have to take control back and give it back to you. That's what I meant to do, was mute.
All right, are we good? There we go. All right, so I'm going to get into the ACI 211 here. This is actually where we're going to get into the proportioning, the figuring out our batch weights, and then doing the corrections for the moisture contents, and into some of the real nitty gritty of actually getting our mix design put together. ACI 211 is the manual we're using for this here. So there's a lot of different charts and stuff that are taken from the 211 and incorporated into the calculations. So this is actually from our level 2 program, the advanced concrete technician program. And this section we'd usually cover in about 2 hours, I think, during that class. And I'm going to do it in about 20 minutes. So we're not going to get into great details on all the math. We're going to see a lot of slides with a lot of math on it, but I'm going to kind of just blaze through all that stuff. If you're interested in seeing that in more detail, I believe we are putting this whole presentation today will be up on the MCA site as a PDF, and you can see that math a little more detailed. So let's get into it. So the first thing we're going to do is we're calculating by the absolute volume method. This method is proportion to yield 27 cubic feet or 1 cubic yard. And each of the component materials occupies a portion of the overall volume that's determined by dividing the mass weight of each material in the mix by the relative density or specific gravity, if you think of the older terminology there. And then we're multiplying by the density of water, which is 62.4 pounds per cubic feet. And so all of this gives us proportions of the volumes of the materials. So we're going to figure out the volumes of the water, the volumes of the sand, volumes of the stone, and base it all into our cubic yard. And you see the example down there. So we got an absolute value of 564 pounds of Portland cement. So you take that 564, you divide it by the specific gravity and the density of water, and it gives us 2.87 cubic feet is how much Portland cement will be in our cubic yard. So almost 3 cubic feet of the 27 will be the Portland cement. So what information do you need when to get started? First thing you're going to need is your specified compressive strength, your F prime C. You're going to need to know your water cementitious or cementitious materials ratio. You need to know what's being constructed. You want to know what country it's being constructed, contractor requirements. You need to know all your ag properties. You need to know your sieve analysis data, your stone sizes. You need to know your fineness modulus. You need to know your relative densities of your sand and your stone, of all your cementitious materials. You need to know the moistures of your aggregates, and you need to know the cementitious properties. So all that's going to be submitted either by your producer, or if you're doing this, on your own, maybe your consultants are getting their materials from individual stockpiles, different stockpiles all over, and doing that testing data themselves to generate all those numbers. So table 4.2.1. So the first thing we're going to do is, once we got our strength all figured out, we need to know what freezing and thawing, what sulfate categories, what low permeability categories, and this determines how severe our conditions are, and so how hard or higher we want to do the design for. So if you look there, mainly the ones we're talking about here in Michigan here are probably our freezing and thawing categories. If you're in an F0, it's not exposed to freezing thawing. And then we go up to our more severe, probably F2, F3 is going to be common for our exterior applications here in Michigan. You got concrete exposed to freezing and thawing cycles and in continuous contact with moisture. F3, the same thing, also using de-icing chemicals. If you have sulfate issues, your soils may have some sulfates in it. You've got some Some severity complexes here. If you're doing some super low permeability, bridge decks or some structural elements, parking structures, something like that, you have some requirements there. And then our corrosion protection, once again, has some requirements here. Do you have steel in there? If you have steel and it's going to be exposed to chlorides, de-icing salts, all that sort of stuff, seawater, then you're once again into a severe category. So this all applies to our strengths. So here we see the requirements for the exposure classes, and it kicks back to these different tables. So you have types of restrictions, whether you have those restrictions or not, based on those things that we were just talking about before. They give the minimum requirements on this table here. So what if we're into two exposure categories? Say we're into a F3 and a C2. So it needs to meet both those exposure classes. F3 requires a maximum water cement ratio of a 0.45 and a minimum F prime C of 4,500, while C2 requires a maximum water cement ratio of 0.40 and a minimum water or F prime C of 5,000. So what you're always going to do is you're going to pick the most restricted of them. So you're going to go with that lower water cement ratio, the 0.4, and the higher strength, the F prime C of 5,000. So we'd be going with our requirements under the C2. So first step we're going to do after that is determine the average compressive strength. So this is our designed over F prime CR is our over design. So once you've got the licensed design professional giving you your F prime C, the next thing is to figure out that required average compressive strength, the over design, the overbuild that is necessary to minimize the possibility of cylinder strength falling below the minimized or specified compressive strength. So you're adding in some extra strength in the design process to make sure our cylinders or our material is always going to meet the strength spec. So if you have strength test records are not available or you don't have a lack of sufficient data, I think Steve kind of touched on this earlier, you're going to have like a minimum number of 30 test data that you've sent in with your mixed design. We're going to use this table here where our F prime C are for the various strengths here. See less than 3,000, 3 to 5, 5,000. You're going to have this F prime C. You're going to add 1,000 PSI to your design, 1,200 in this range, and 1.1 factor plus 700 in your over 5,000 range. So we're adding in quite a bit of extra strength there since we have no data. When field strength records are available and they're not older than 24 months and they span no more than 45 calendar days for a classic concrete within 1,000 PSI of that required for the project, you can calculate the simple standard deviation, determine the required average compressive strength F prime CR using this table here, 4.2.3.3. So you can see there's a little bit different, a little bit easier on here. Looking at this calculation real quick here, the K, we're going to talk about that in a second here, but that's a factor. The S sub S is our standard deviation. And what you would do is you do both of these calculations for whether you're doing this one or this one. You do them both, and then once again, we're going to pick whatever one is higher, whatever is more critical. If you have field tests that give you some information and you have your standard deviation is not 30 or more, but 15 or greater, you can use this table here. So this was that K factor that we were talking about on the previous page. So if you got 15 tests, your K is going to be 1.16. You got 20 tests, 1.08 is your K. And then if you got 30 or more, we'll have a 1.0. So you got enough there that there's not an increase in the K factor. So in 1.2, the methods provide a first approximation of proportions intended to be checked by trial batches in the laboratory or field and adjusted as necessary to produce the desired characteristics of the concrete. So this is going to give us our batches. We're going to get our weights, but you still need to do those trial batches. You still need to do laboratory and field testing. You need to get good consistency, good see that it works good for you. This is just the basics. This is a starting point. And the selection 2.2, the selection of concrete proportions involves a balance between economy and requirements for placeability strength, durability, density, and appearance. The required characteristics are governed by the use to which the concrete will be put and by the conditions expected to be encountered at the time of placement. These are characteristics that are specific to the job. Whatever you're doing, you need to keep in mind that stuff's got to work for the actual job that you're using it for. So we're going to get into a little basic run through here. So our type of structure we're going to work on is a warehouse floor. It's 5 inches thick. It's not reinforced. Our required F prime C is 3,500. We have a standard sample deviation of 644 PSI, and that was based on 30 tests. So we're throwing that K out, and we have a standard deviation of 644 known. So we're kind of doing this the quickest, easiest calculation for our designed over design. We've got some coarse aggregate properties here. So we know our nominal size, our relative density, specific gravity is a 258. We've got our total moisture. We've got our absorption. We've got our free moisture. We've got our bulk density. So that's all going to go into our 211 form, and we can use that in our calculations as we work our way through our 211 form. You also see the fine aggregate properties there. Real quick, just to talk about maximum and nominal maximum size. So we're referring to our aggregates here. It comes up on the form when you're picking the proper table. You need to know your maximum, nominal maximum size. So a maximum size is smallest sieve opening through which the entire, the amount of aggregate is required to pass. So that's, if you're looking at in your sieve requirements, that's your 100%. The nominal maximum size is the smallest size sieve opening through which the entire amount of aggregate is permitted, but not required to pass. So that's generally the one just to the right of it. So it's going to say 90 to 100 or 95 or 85 to 100. That's your nominal maximum size of your aggregate. And that's what you're going to be choosing. That's the one you want to be looking at when you're choosing these things. So therefore, your choice of your nominal maximum aggregate size, in no event should the nominal maximum aggregate size exceed 1/5 the narrowest dimension between the sides of the forms, or 1/3 of the depth of the slab, or 3/4 of the minimum clear spacing between the individual reinforcing bars or bundles of bars, or if you got pre-tensioning strands and a precast piece, you got to have that clearance. So in this case that we are working on, 1/3 of 5 inches is 1.67 inches, and therefore the proposed 1 inch max size aggregate is okay to be using in this mix. Pretty much any 6A would have been fine. So here's the calculations for that F prime CR, the required overcorrection. See there are 3,500 PSI, the correction factor. That gives us this number. Then we do the second calculation. You got the 233, our K is 0 or is 1, and our standard deviation, and I go through that, and you get the 4501 PSI. So we're going to pick the higher, right? So we got 4363 here, but 4501's higher. That's the one we're going to pick. And you always round to the nearest 500. So we're going to be designing for 4,500 PSI. So we got that figured out. Now we're going to look for our mixed proportions for the first approximation. You're going to complete the ACI table information. You're going to calculate your dry batch weights. You're going to calculate your dry batch volumes. Then you're going to calculate your saturated surface dry weights. And then you're going to adjust the batch weights for the actual moisture conditions. So we'll run through this kind of quick here. Just to show you the different moisture conditions, aggregates have internal voids or pore structures that at any time may or may not contain water. That's the absorbed water. Depending on the moisture content, the 4 possible conditions for the aggregates are as follows. You have oven dry. That's no moisture at all. That's what you're going to do in the lab. You got air dry, so that's sitting out. Maybe you got some samples in the field, and you're going to spread those out to air dry before you break them down into testing size samples. Air dry is capable of absorbing additional water. So you kind of see these little circles over here, kind of looking at it. Saturated surface dry, that's fully saturated, neither absorbs nor contributes water to the mix. So that's kind of what we're shooting for in our batch weights, is to be at a SSD condition. And then wet is contains an excess amount of water. So that's our water that's outside of the samples. You can actually see the water on the aggregates themselves. So here is the 211 form, and we're kind of looking at this and we're going to go through a little bit, but keep in mind, you know, most producers and contractors, they have software or they have an Excel spreadsheet, and all this stuff is done for them. There's not a whole lot of people still going through and using this 211 sheet to get the calculations, but we're going to go through it so you just kind of get a background of it and to know where those softwares and spreadsheets came from. So as we were talking about our stuff before, here's where you would input all of that aggregate data that we looked at earlier. Here's where you'd enter all that fine aggregate data we saw earlier. And then you're going to grab all these numbers are from the 211 tables. So we looked at a couple of those tables earlier. We're going to look at some more of them. And you input that stuff into here. Once you have all of this filled out, then it feeds down into the bottom and you work your way through these calculations. You come back here. So you got your waters and stuff here. You go to your volumes, and then you get into the SSDs, then you correct for your fine, and then we get into the bottom part. So you'll get into this real quick here. So here we're showing that we filled it all out. We have our SS, we got 30 tests. Here's what we were doing. Once again, all that stuff. We pulled from the ACI tables our slump, our air, our water, our volume of our coarse aggregates, our water cement ratios. So you get from 6.3.1, this is where we find our slumps for various types of construction. So you'd look at what kind of thing you're building. So we were building a pavement slab. So your max slump is going to be a 3-inch with a minimum being a 1. This doesn't take into account that if you're using some admixtures, more than likely a mid-range, that's going to allow you to bump up an additional 1 inch. So we would probably actually be looking at a 4-inch max. Most modern concrete's got a mid-range in it, so we can get a little more slump. And then on 6.3.3, this gives us our mixing water that we'll plug into our chart, and it gives us our air content requirements at different slumps and at nominal maximum aggregate sizes. So we're going to look in here and warehouse floor slab. So we're in the non-air entrained. Our max aggregate size was 1 inch. We were looking at a slump of a 3 to 4. So you come over here and you find that we would have 325 pounds of water in what we're working on in this example. Let's see the other. Here's make sure if you are doing exterior, make sure you're using the air and train part of this table. Common mistake in the class. And 6.3.6, here's where we get the volume of our coarse aggregate. So once again, we're looking at our nominal aggregate size, which was a 1 inch. And then you have your volume of oven dry rotted coarse aggregate per unit volume. So this is based on the fineness modulus of your fine aggregate. So you would have to have that information. So we looked at, I think we had a 2.5 was on that previous slide there. So we're at 1 inch. And the 2.5, we'd have to interpolate a little bit. So we'd be in between the 0.69 and the 0.71. So we'd be using a 0.70 for the volume of our coarse aggregate. The relationship between water cement or cementitious materials ratio. We go by our compressive strength here and whether it's non-air or air. And we'd be down here. Interpolation may be needed once again to get our water cement ratio. The maximum permissible water cement or cementitious ratios for concrete and severe exposures. So they have some special conditions if you're in severe exposures. So you'd be looking at these water cement ratios. And once again, we're always going to take the most critical or lowest value on our water cement ratios. When looking at the water cement ratio for both strength and durability for exterior on exterior cold slab in a cold weather environment, that's always the most restrictive. I just said that. I haven't been through this one in a while. So here we're looking at the fundamentals. So we've inputted our water cement ratios. We've got our mixed water from the table. We got our volume from the table. We got our bulk density from our supplier data. We're going to input how much air. So we got this much air. And then you do a quick little math through all this and you get these volumes. So we end up with 3.18 cubic feet of cement, 5.21 cubic feet of water, 10.9 cubic feet of coarse aggregate. Our air ends up taking up 0.41 cubic feet. That gives you a subtotal of 19.7. Subtract that from 27, because there's 27 cubic feet in a cubic yard. That leaves the leftover is 7.3. That's how we figure out our fine aggregate. So we bump the 7.3 volume of fine aggregate times the specific gravity and the density of water to give us our weights of our sand there. Then we got to adjust that for the SSD. So now we're going to account for the moisture that is in the aggregate. So that's where we have this absorption value. This comes in right here. Adjust our weights. So this doesn't change. This doesn't change. We're adjusting our coarse aggregate. We're adjusting our fine aggregate. And this gives us our total weights. Divide that by 27 and you get your density of your concrete. So we're going to end up at a 147.3 pounds a cubic foot for our density. So that's SSD, but we got to keep in mind that these piles are outside and there is some free moisture that's on these piles. There's some extra water out there. So we don't want to change our water cement ratio. So what we have to do is subtract that water, that is the free water on our piles, from the total amount of water we're putting in our mix to get our final batch weights. So that's what this math is here. We got our free moisture times our dry number. That gives us an additional 7 pounds of water, which increases our weight to that. 1809 was our SSD weight, so we're adding 7. So we've adjusted, we got the weight of water there. We've adjusted the weight of water here, and that gave us 21 additional pounds of water. So we need to subtract that from our total amount of water in our original mix. So we end up with a net water, 304, converting that to gallons, 36 gallons. So this ends up being our batch weights that will actually batch out based on the moisture conditions. And here's the total completed form. So kind of see how we work through this whole form. All the data up here, you work through here, you come back to here, work down here, work all the way across. We end up with our final batch weights. And so here you see the design weights. We ended up there. We ended up with our batch weights. They're adjusted for the moisture here. We've got a slump of 3 to 4 inches. We got an error of 1.5%. We got a density 147.3. So are we finished? No, we're not finished. The mix always needs to be checked. You need to run trial batches. You need to be running your strength test. If you're needing to open early for traffic, you're probably going to make some beams and get some flexural strength tests. You're going to be checking their air. You're going to be checking your slump. You're going to be checking your density. And then the biggest one is just, is it usable? If you're going to be using this in a tremie or you're going to be using it in a pump, is it going to be good placing in that pump? Is it going to go through the pump? How does it look? Does it have good appearance? Is it workable? Is it finishable? How long will it take to set? You may have all sorts of extra tests that you may need to do afterwards. And this is in addition to all the aggregate testing we did beforehand. So that's the really, really fast version of the 211. I think the next slide here, we get into some more of the reviewing. I'll go through real quick before I give this back to Steve here. I would be often in the consulting side of things, kind of the submittal process for us. Often when we were doing these special provision for local agency projects, it would come to the QC administrator to kind of make this whole process happen. So that QC administrator is usually the one that's gone through the 211, has gone and got all the data from the supplier, from the producer. Your ready mix guy is going to submit you to that QC administrator. Then that QC administrator takes all that stuff that we've been looking at, and we're going to look at further here in the next few slides, compiles it into the QC plan. And so there'll be a hierarchy cited in the QC plan. The contractor or the project managers at the top, then the QC manager, and then all the data will go down to the other personnel that are involved. And then the QC plan will tell you about, the hot and cold weather conditions, any stockpile conditions, all that stuff is submitted all into the QC plan. Then you would have appendices that would have all that aggregate information, all the mix design information, maybe equipment records, maybe personnel's certification records. That all gets put into one big QC plan. Then that QC plan would go to the engineer or maybe the QA administrator. They would review all of that. They would kick it back if you were missing any information, or they wanted something clarified, or they saw something was wrong. The QC plan administrator, once again, would go through it, do those corrections, send it back to the engineer, and then they'd finally approve it. And that was generally how you got your mix design approved on most of these smaller type of MDOT-led projects. So let me give control back to Steve here.
All right.
Steve?
Yep.
Back.
Okay.
Was that clear? Was I good?
Yes. We've got a question. How many days mix design must be submitted, reviewed, and approved before using it on site?
Yeah, and I would say it had to go through, I'm not sure if there's like an actual specific, it might be 7 days, but it would definitely have to go back to the engineer first. They would have to make any of the approvals finalized.
Yeah, that is, it's in the spec. I think it's 7 days. I think you're right about that. And the question also asks, please discuss a summary requirement for the pre-con meeting. What would you recommend they discuss at a pre-con or pre-pour meeting?
Right, and that's an important thing. I've been to a lot of pre-con meetings where we kind of just zip through all of the stuff we're kind of talking about today, but we never talk about, you know, pumping, how the testing is going to be done at the pumping. I would say that's a very important thing to discuss, whether you're testing first, then placing, and then testing after a paver is being used. Another important thing to talk at the pre-con meeting, besides the whole mix design thing that we just went through and all the aggregate submittals and whatever other submittals are going on. Hot and cold weather conditions, another important thing to talk about at your pre-con meeting. And any approvals and who's checking things, you know, who's going to be in charge of this, who's going to be testing that, you know, other important things to do at your pre-con meetings. Whoever's running the meeting really needs to make an agenda that includes everything that needs to be talked about.
Yeah. There is, I believe it's 7 days. I didn't pull up the special provision, but I believe that all the QC plan needs to be approved at least 7 days prior to the start of anything. So then, and the JMF forms are in that QC plan, like Dave said.
And also, like just to add on to that, he had said pre-con meeting. I'm actually more talking about the pre-placement meeting. The pre-con meeting would have preceded this. This is more of a pre-placement meeting.
Yes.
Just to clarify that.
Yeah, that's a good point. I call it a pre-pour meeting, or pre-placement meeting. Yeah, the pre-con meetings are the bigger picture. We're talking specific to concrete. That's would probably include, you know, it doesn't usually has one of the prime contractor representatives, but includes concrete sub, you know, testing firms that are doing concrete testing, you know, the QC plan administrator, and those folks. That should be separate and after, you know, those pre-con meetings essentially. All right, so once the mix design has been developed, like Dave went through very quickly, the basics of an ACI 211 process. It's on that JMF form. JMF form gets submitted typically with the QC plan, like Dave said. If there are changes, additional mixes that need to be developed, then additional JMFs would have to be included and submitted for review. Obviously, if you're switching to a different mix design, you've got the test data hopefully to back it up. But that requires review. And then that annual verification method is for an MDOT specified recipe mix, not very common anymore. It was in the past, but they've gotten out of that with downsizing and everything else. That is not as common anymore. They don't want to be in the mix design business, MDOT. So we're going to go through a quick mix design submittal. This is, again, just a portion of what goes in that QC plan. The summary page and then explaining everything. You know, we've got 4 different mix codes here being used in this particular project. Got all the basic info here, project numbers, etc. Then you got your JMF form for that particular one of 4 in this case. And then after the JMF comes all your backup data that proves that this mix has the desired fresh and hardened properties that we want because we've probably used it on a previous project. Most concrete producers do not reinvent the wheel every time they, load a batch of concrete to send it to your job. They usually have a very good handle on how that material has performed. They generally don't do massive switchovers of their materials very often. Every once in a while, you'll get them switching out a source of sand or coarse ag, or maybe an admixture switchover if they're unhappy with a particular supplier or something. But in general, they usually have a good performance of the materials that they use. So strength data on that mix, admixture certification, your sand gradation, coarse gradation, mill report for your cement as well as slag cement, your ASR, ASTM 1293 data. Most of them have the year-long test, and they have a year off, and then they got to run it again because the data is good for 2 years. There was discussion of requiring every year those tests be done. In other words, the data only be good for 1 year. That has not been proposed as a change as of yet. There was some discussion, but we have agreed on 2 years, so you do get a year off if you're a sand producer from always having to run a test. Their NRMCA plant cert, the plant itself, or plants, if you're using multiple plants to supply a project, each one has an NRMCA certification that go through that certifies the plant and their ready mix trucks. Portable plants also have this cert. Scales, scale calibration. If it's a portable plant, anytime the plant is moved and set up again, or 6 months is how long those scale calibration reports are good for. Same rule applies to permanent plants, ready mix plants. Admix calibration is required as well, certification on that. Water meter calibration, so that they're, most of them are, dispensing, either it's a volumetric, dispensing by gallon, or they weigh it and do it by weight. And then the stockpile management plan. Each concrete producer has to have a stockpile management plan that shows their process and how they minimize segregation, how they minimize contamination to the materials, et cetera, et cetera. So what is their plan? Do they have the precast concrete blocks dividing each pile, and they have bins essentially, or areas in the yard so that the materials can be piled up without the toes of those slopes interacting with each other, and one material getting mixed in with another in the yard. So, things like that should be detailed in that plan. And that's pretty much it. That's what all goes into the actual JMF submittal that gets put in that QC plan. Again, that QC plan has 26 things in it. The JMF information is only one piece of that. But those JMFs, those mixed designs are all about concrete strength. That's the main thing. We want to ensure that the concrete gains the proper strength. And we have the test data that proves that it does that. But in doing that, we have to balance slump. Obviously, the contractor wants a particular slump so that it has a workable mix for whatever machine or equipment they're using. And if it's exterior concrete, like almost all of MDOT's above grade, concrete requires then an air content in the 5.5 to 8.5% range. And the more air you put in, your strength decreases, but your workability increases as well. So all this is balanced. The density, obviously we want good, hard, durable aggregates that makes dense concrete, and durability in general. Where we've had durability problems in concrete, it is usually not the aggregates. We haven't had many aggregate problems. There's a slight amount of ASR in certain sand sources throughout the state. Generally not a main mode of failure that we've seen. We generally have good coarse aggregates that we've used now for the past 30, 40 years in the state. But where we've had durability issues, it's like Dan talked about yesterday, those supplementary cementitious materials really help get us better durability. But that's a balance as well. When you use lots of supplementary cementitious slag or fly ash in the winter in cool temps that we're starting to see now, it definitely does slow down the set of the mix. And also have to balance optimized aggregate gradation. We didn't talk about that in this seminar, but that is in high performance concrete, either bridge decks or pavements. requires that intermediate aggregate, and that's a balance as well. Having to add that in there because it changes what you can do with your plant because you're adding another material as far as bin space in plants. Most of the pavers have either modified their plants to accommodate 3 aggregates, sand, intermediate, and coarse stone. But not all the ready-mix plants are set up to easily handle that intermediate stone because they have to balance their other customers' needs with different other types of aggregates, rounded, river rock and other sizes and other materials. So that is a balance as well. But optimized mixes generally do make very good concrete. So that is the plus. And then that JMF form 1976 does require all that backup documentation. It's not just submittal of the 1-page form where you fill in all the numbers, but those are all approved sources, and you have that backup information that you have to submit with that mix design to make sure all your I's are dotted and T's are crossed, because that's what is going to be looked at to make sure that all the numbers on that form are represented in the backup documentation and all the math works out. And there's nothing missing, because that's the checklist that they go through essentially is looking at that MDOT form 1976. So we got done a little early today. We didn't want to bore you with the ACI 211 procedure. Dave went through that fairly quickly, but that is something that is done whenever new mix designs are completed. But if you have any questions now, please feel free to type them in the Q&A window. We'll try to answer them to the best of our knowledge during the time we have now.
Yeah, and I would add into that, if you want to get deeper down that whole 211 and you want to know, maybe you're a producer or you're a QC administrator and really want to get into the weeds of all this stuff, I highly recommend coming to the level 2 program here at the MCA. We cover about 3 or 4 days worth of this kind of information and what goes through all of this process, a lot more detail. And if you really want to know the ins and outs of all of it, I'd recommend coming to that class.
Yeah. Yeah, this was definitely an overview. We're not teaching you how to do a mix design, but just so you're knowledgeable of where those are coming from. And again, concrete producers do not reinvent the wheel very often. They're typically using a mix that they have a very good history with, a very good confidence with how it's going to perform in various conditions. And they definitely know what they're talking about when they tell you about their concrete. So, but if they do have to run through the process, that is the process they run through to develop a new mix design and do all the trial batching in the lab, there is an option in the MDOT spec to you, if you're using that mix on it's not been approved, so it would be on a residential or commercial or other type of job, not an MDOT job, and it's the exact same mix they plan to use on an MDOT job, that test data that they're getting from their testing consultant or whoever's doing the testing on that other job is valid test data that can be used. You don't need to always do a trial batch if it is a mix you're using for other customers and you have valid test data. So you could try it out on your residential or commercial customers first, and then get the test data and the 28-day breaks, or if you can get the early breaks, if they're within the range that MDOT allows, then that can be used as well. But you don't always have to do a lab trial batch when you're doing a switchover of materials. Okay, that's all we've got today. Exactly 1 hour. It's 11 o'clock. Our contact information is there. Hopefully everybody was able to download the handouts on our webpage. I added it about 9:45 this morning. Right there is the handouts from today. So these are the 3 from the last 3 days. We'll leave those up there. Feel free to download any of the past ones we've done. If you have any questions on those, let us know. We do have one last question here. Is temperature control technique used during roller compacted concrete? Great question, Richard. Roller compacted concrete is something we talked about last year during our in-person local seminars. And that's something we'd be happy to do another virtual learning webinar on. But as far as temperature control, that's all done in a concrete plant, whether using chilled water or heated water to influence the temperature of the mix. As far as during compaction, there is no temperature control or worry about temperature like there is with asphalt, because we're compacting it while it's still fresh, and then it will kick off and hydrate because it is regular concrete. It's just at a much lower slump. So to answer your question, Richard, there is the ability to use chilled water or heated water. Various limited availability of hot sand during the winter months, but that is an option too. And but most of those plants it's much easier to influence the temperature of the water to influence the temperature of the mix. Another last question here while folks are on the line. Specifications state not to exceed the designed water cement ratio. That's correct. If all water is incorporated in the mix, then all water has been used. Can you still add water in the mix when it arrives on site, as it will exceed the water cement ratio? The answer is no. If you have added all the water up to the maximum that's allowed in the spec, then no, you are not allowed to add additional water into the mix to influence the slump. You'd have to introduce some water reducing admixtures perhaps in order to increase the slump if you have all the water. So most concrete grades that MDOT does has a maximum of 0.45 water cement ratio. And sort of in order to have a workable mix, most concrete producers typically will batch at least some amount of water reducer in order to get the desired slump for the contractor and yet still be under that 0.45 water cement ratio. So Eduardo, to answer that question, no, if all the water's been added at the plant and you're at the maximum water cement ratio, if that truck shows up on site and it is low in slump, it's dry, the contractor would like to add more water to get a workable mix. No, they're not allowed to if all the water, but that math needs to be checked on that actual batch ticket to verify whether or not you are at your water cement ratio max. So good question.
Yeah, and he goes on there. I was just going to mention this, Eduardo, is check the tickets. Oftentimes the plants do trim back some water for just such an occasion. So they won't add all the water. They'll trim 3 or 4 gallons, and you got to check the ticket to make sure they did do that though. And you got to actually look at those batch weights compared to the trimmed batch weights to see if there is any water you could possibly add on site. Most of the time they don't trim much, but sometimes, if they know a history of the mix and travel time, and sometimes it needs another gallon when it gets to the site or whatever, they will trim some water, and make sure to check the ticket to see that they did that before you do add that water.
Yes. Yeah. If your mix design has a maximum water cement ratio of 0.45 and your actual JMF, your proportions, theoretically, batch that water 0.45, and then yeah, if they didn't hold back any water, like Dave said, then they put it all in and you're not allowed to add. But you can't reject a truck or tell them they can't add water if you don't check the ticket first to see what was actually put in. Because we didn't talk about this, and the variability that you can sometimes see in batch weights, because once they put it in, they can't take it back out. And sometimes things happen and scales aren't perfect, and the hoppers, and valves and everything don't close instantly necessarily. So sometimes either extra or less is put in. And so you need to check, but it will weigh it. It will measure it. It's just, it's not an instantaneous process. So you check those batch tickets to see if all that water is in there or not. So I would, do not reject a truck or tell a contractor he can't add water if you haven't checked the ticket first. Good questions, though. Very good questions. Anything else while you got us on the line? Other than that, enjoy the rest of your day and feel free to contact us with any questions you have in the future. We appreciate everybody's attendance this week and wish you all the best and take care.
Yep. Thanks, everybody. Have a good day.